Hey everyone, let's begin our next topic. We're in section 3.8, exponential growth and decay. We're also going to learn about Newton's law of cooling, which is the same sort of thing. Most of what we're going to be doing is not actually calculus, it's going to be arithmetic, but it's all motivated by calculus. We're using a model to determine the population at a certain time t. And the way that we set up our model is we use calculus. So one thing that we do, really the crux of our model, is we assume that the growth rate of a population is proportional to the population for itself. For example, if you say something like, the population doubles every 10 minutes, right? The population growth rate depends on the number of individuals at that time. So the way that we assume this is if we let t equal the time and let P of t equal population at time t, then we can assume that dp over dt, right, the rate of population growth over time, is proportional to the population at that moment. Right? And the way that that winds up working out, and you can test this, I'll write this again, dp over dt equals k times p, winds up being that p of t equals p of 0, right, whatever the initial population was, times e to the kt. That is our model, right? So this is the formula you need to memorize. So let's consider a problem, right, where there are initially 100 cells in a petri dish. The population doubles every 20 minutes. Right? We want to be able to model the population at a certain time t, right? After how many minutes? After, 1,000 minutes, what's the population, for example, right? So what we do is we say, let t equal the number, right? We always want to look at the units, right? So if we're talking about minutes here, then we always want to say let t equal the number of minutes after observing, let me make that a little clearer, after observing 100 cells, right? So that way, when we observe that there are 100 cells, that's t equals 0, right? And then we also want to let p of t equal number of cells at time t. All right. So by definition, right, if t is the number of minutes after observing 100 cells, then when we initially observe 100 cells, that's time t equals 0. So p of 0 equals 100. It's very important that you understand that. If you don't understand that, then go back and pause the video and go back and watch the last minute. Right? So we know then that p of t, right, by definition is p of 0 e to the kt, but we also know that that's 100 e to the kt, right, because we solved for p of 0. So we got one data point, right? We got p of 0 based on the observation that there are initially 100 cells. But how do we solve for k? Well, we need that second data point, right? Well, we know that after 20 minutes, there are 200 cells, right? And we can use that to solve for k, right? Because we know on the one hand that p of 20 equals 200, but on the other hand, by definition, we have that, right? Just plugging 20 into our model gives us this. This is the actual data point, right? So we're just going to solve for k at this point, right? So here is where ln is going to come into play, right? Divide both sides by 100 to get this. But then we're going to take the ln of both sides, and I'll do it out this one time, but next time I'm going to just sort of not write the ln down, at least not on the left side, right? Now we know that the ln of e to the cancels itself out, right? They cancel each other out, right? So we're just left with that. If you're not sure how that happened, then go back to section 3.6. Anyway, we solve for k, and we get that. right? So now we have a complete population model, right? The population at time t is going to equal 100 e to the kt, but instead of k, right, we're writing this value we solved for. So we get that. So this is a final answer, right? Mastery, 10 out of 10, if all I'm asking you to do is find the model for the population, right? You can plug in 1,000 and compute the number, and it'll tell you how many cells there are at time t equals 1,000, right after 1,000 minutes. Just to let you know, you might see this in a bio class. If you don't like the whole e to the ln thing, then you can do some little trickery like this. Right? So I will never expect you to do that, but if you want to, then you can. All right, so let's look at example 2, right? Suppose that we have a population model, right? We want to model the number of people in the world and use it to predict the future population, right? So suppose that we know that the world population in 1750 was 790 million. Then in 1800, it went up to 980 million, right? Can we use an exponential model to predict the population in 2000? Also, when's the population reach 1 billion people, right? So as always, we want to, right, see how I say let 1750 equal times 0? We want our initial observation, the time of that initial observation, to be time t equals 0, okay? So you want to let t equal number of years after 1750, okay? And I'll say ends let p of t equal the world population at time t. And I'll just write millions. All right, so let 1750 be times 0, right? Do you see how that just follows from this definition? Right? So p of 0 is going to equal 790. We're not going to write the million, right? And you don't have to write this down, but just to be crystal clear, that means that p of t equals 790 e to the kt. We got our first data point, we need our second data point, right? 1800 corresponds to t equals 50, p of 50 equals 980 million, right? That was given to us, right? So p of 50, on the one hand it equals 980, on the other hand it equals 790 e to the k times 50. Again, we have everything is, a number except for k, so we can solve for k, right? So we're going to get e to the 50k equals 98 over 79. Take the ln of both sides. I'm not going to write it on the left. It's just going to be 50k. On the right, it's going to be ln of 98 over 79. So then we're going to get k equals 1 over 50, ln of 98 over 79, right? And so now we have our answer. Remember, this is not our answer, right? This is just solving for k to get our answer, right? So the population, so the population at time t equals, it's going to be 790 e to the 150th ln of 98 over 79 t. Lower that a little bit, right? Note that all this is in the exponent, right? So first off, right, if we want to find the population at 2000, right, what are we going to do? Well, we just plug in 2000 for t, right? You get 790 e to the 150th ln of 98 over 79 times 250, right? Note that this cancels kind of nicely. And if we do it out, right, if we just you won't have a calculator, but if you enter it into Google, then you get this, right? On an exam, you would leave it like this, right? On a quiz or an exam, you leave it like this. But this winds up being, I'll just say approximately 2,321 million, or approximately 2.3 billion. Right? Not a great or terrible estimate. Right? Like, yeah, it's off by several billion. It's off by like a factor of 3 or 4. But you know, it was taking data from 200 and 250 years ago. That's not so bad, I think. Anyway, what about the second problem, right? When does the population reach 1 billion? This is a little bit more involved, right? Because what we want to do is we want to let P of t equal 1 billion, or in this case, 1,000, right? Right, so we're going to let P of t equal 1,000, which is to say we want to let 790 e to the 1/50th ln of 98/79 t equal 1,000, right? See how once we have the population model all complete, we can answer any problem about the population? Right, so anyway, we do this, divide both sides by 790. This is going to be 100 over 79, right? I knocked off those extra zeros. Take the ln of both sides, and we get 1/50th ln of all this. And then we multiply both sides by 50. And we get ln of this times t equals 50 ln of this guy. And then our final answer is this. Now, on an exam, you would just leave it like this. Right? There are ways to simplify, but it's not really worth it, right? But just to show you what this would give us, right? If we put this into a calculator, again, I wouldn't have you do this on an exam. We have 50 ln of, was that 179ths? Yeah, 179ths, yeah. Divided by ln of 98/79. Let's see what that gives us, right? 54.68, okay? 54.7 or so. So, so t equals 54.7, right? Plus 1750. Equals 8, I guess that's 1,804.7. So the population reaches 1 billion people in 1805, right? This one's very similar. I'm going to ask you to try it. But as you'll see, you'll get an answer that's a bit of a better model for our current population. And that makes sense because we're using data, you know, from much more recent years.